Hey there, in this video we're going to learn some shortcuts for creating arrays. So far we've created all of our arrays by hand, and you can imagine that gets pretty tedious if the array has more than just a few things in it. So we've seen things like a numpy.array 1, 2, 3, 4, 5, and I had to type out every single thing in that array. It works for small stuff, and it works if I need to control element by element what's in there, but it's kind of awkward. You might be thinking, well, maybe we could use some Python code with for loops or while loops to build up a list and then put the list in here. Yeah, you can do that, but there's actually an even better way to do that. So that's why I haven't shown you the other approach. What we're going to do is use some functions built into NumPy. The first one we're going to look at here is a lot like the range function from base Python. The difference is it lives in the package NumPy, and it's arange, which stands for array range. So let's look at the documentation here. I could open up the contextual help, but instead I'm going to do a different shortcut. I'm going to hit Shift Tab a couple times, and that pops up the very same help message in a floating box. And that way I don't have to keep redrawing my screen here. So looking at this, we can see arange has an optional start, always wants a stop, optional step. And even you can change the dtype if it's not what you want. So if I give this just a single argument, it'll act like range with the single argument and it'll only have a stop. And it'll do a default number of steps, which I think is 10. It's integer steps by default. Okay, so if I had 10, it would do 10 steps. If I had 11, it would do 11 steps. What we're going to do here is start, stop, step, because usually you're going to use arange if you want to create a sequence of data of increasing values and you want to control what the step size is. So I can say start at 1, end at 10, and take a step size of 0.1. Unlike range, which only works with integers, arange will work just fine with floating point numbers, and by default will give you an array of floating point numbers. So if I run this, I have about 100 values, 1 up to but not quite 10. So just like the range statement, arange stops right before it reaches the stopping value. Now in this case, everything's equally spaced, like you can divide this interval equally by steps of 0.1. But your step size does not have to equally divide your interval. Let's say my step size was 0.13. Now let's look at what array I'm going to get. So I get 1, and I take steps of 0.13 all the way up to 9.97, which is really close to 10. It's not 0.13 away from 10. It's got as close as it could. The next step would take it past 10, so that's where the array stops. So the disadvantage of using arange is, without doing a separate calculation, it's not obvious what's going to be the last value in your array. The advantage is you get a fixed step size. So a close cousin of arange is the function named Linspace, and the advantage of Linspace is it lets you control the number of steps you get. Another disadvantage with arange here is without a second calculation, it's not clear how many things are in my array, but with Linspace I can control that. So if we look at the documentation for Linspace, start, stop, that's pretty much the same as before, and number of points, by default 50. We don't usually need anything else here in the arguments, maybe dtype. So if I want to go from 1 to 10 and I want to specifically take, say, 12 steps, I can do that, and it will calculate what the step size needs to be to make sure that I start at the start and stop at the stop. Notice that we do make it to 10. We get to include the last point when you use Linspace. So these two, arange and Linspace, are really handy when you're doing things like making plots and you want to create a whole bunch of values from the beginning of your range to the end of your range. The difference being, do I want them equally spaced where I control the spacing, or do I want them equally spaced where I control the number of points I'm going to get? Another common thing with an array is you want to create an array where all the values are the same to begin with. Typically these values would be 0 or 1, but they might be, say, 7. So if I want to make an array that's all zeros, I can use the command np.zeros. We look at the documentation there. We've got shape, dtype. You don't really have to worry about order. That's just sort of an implementation type detail. So shape here is like the length. So if I want 10 zeros, I'll do zeros 10, and it will give me an array of 10 zeros. You'll notice that these are floating point zeros. So by default, all these functions will try to make floating point values for you. If I want to force this to be integers, I can just add a second argument here for the dtype, and now it'll make an array of 10 zeros. Closely related to that, we have np.ones, so I can make an array of 10 ones. Let's say I want an array that's all 7s. There's two ways I can do that. I can multiply my ones array by 7, or I could add 7 to my zeros array. It doesn't really matter which approach you take. But these are ways to get arrays that are all the same. The last thing I want to look at is how we can make higher dimensional arrays. So NumPy can have 1D arrays, that's what we're seeing here, but it also has 2D, 3D, really no limit to the number of dimensions the array has. In physics, you're usually not going to see anything beyond 3 dimensions. And actually, most of the time, we're going to only go up to 2 dimensions. So let's look at how we can make a 2-dimensional array. Let's start by manually typing out the entire array. We can do this by feeding numpy.array a list of lists. So I have a list that includes itself some number of lists. Let's say I want to make a 3x3 array that perhaps would represent a matrix. So in the first list, I could have 1, 2, 3. That would represent the first row of the matrix. 4, 5, 6, 7, 8, 9. And so when I create this, we can see that it even prints out in a nice sort of way, showing us what looks a lot like a matrix with 1, 2, 3, 4, 5, 6, 7, 8, 9 in it. Of course, it can be tedious to create large arrays by hand. Let's say like this represented, say, some kind of grid that we're going to do a big calculation on 100 by 100 values. We would not want to type that out by hand. Instead, we could use zeros or ones to build our grid. Let's look at zeros just for the example. So I could do numpy.zeros. And if we looked at the documentation, remember the first thing in here says shape. It didn't say length, but it said shape. So shape tells us what we want our array to look like. So if I wanted a 3x3 array, I include a tuple in here. So don't forget about those inner parentheses, 3x3. And that would create a 3x3 array of zeros. If I wanted to make a 3-dimensional array, I could add another value in here. Say I wanted think of 2 slices that are 3x3. It gets kind of weird trying to represent it on your computer screen. But this would represent like a volume that was 3x3x2. Like I said, most typically we don't go above 3 dimensions. Now, if you're wondering what happens if I leave off those parentheses and I do zeros 3, 3, I'm going to get an error message. Particularly saying here data type not understood. It's specifically the second 3 here. When you write it this way, it's going to try to make an array that is 1-dimensional, 3 zeros long, and it's trying to use a data type of 3, which it can't interpret. It's expecting something like int or float or complex. It sees 3 and it says, I don't understand that. That's why you get this error message. So what has happened is you need to include this inner set of parentheses because you need to pass a tuple. All right, so in this video, we've looked at some ways that we can quickly create arrays using arange or Linspace to give us an increasing sequence or a decreasing sequence if we put the starting value larger than the stopping value with a negative step size. That works just as well. The difference being that arange lets you control the step size, whereas Linspace lets you control the number of steps. And then we looked at how we can make arrays where all the values are the same, and then we could modify them afterwards using either zeros or ones. And we looked at how we can make 2-dimensional arrays, either manually as a list of lists or by passing a tuple into zeros or ones.